Good day, folks. I'd like to talk to you today about a concept I've visited from time to time. Basically RF resonance, but I'd like to clarify basically the energy mechanisms. How we can use RF resonance to transfer energy over efficiently. Don Smith and his ways tried to hit on that by basically building resonant transformers, the equivalent anyways as RF. So instead of basically building a typical EM transformer, he built basically the equivalent of the antenna version, where you've got a primary loop antenna and then the secondary loops are the equivalent of the receivers nearby which could hear the field. So all at resonance, by the way. So essentially he suggested something which people are having a real hard time with. He was saying, never mind all the complex issues you may run into, just pick any random length, let's say 100 feet for your primary, as long as your secondaries are 400 feet windings, you stick to whatever resonance the wire is. Now the issue with that, it's just like a swing. I mean, you can push it not at its optimal and it's still going to give you action, but not as much as if it were its resonant point. So in other words, in radio circuits and various oscillator circuits, we have to do more to it than just hook up a coil to a battery and then it's just going to self-oscillate. We need some sort of feedback mechanism that takes into account usually the inductive value of the coil, the capacitance and the resistance, and on it goes, and then we have a resonant frequency that it will tend to feedback with, assuming you have some sort of triggering and feedback mechanism for it. So what Don Smith was saying is, okay, just feed whatever high frequency you want into it and it'll just adjust itself to whatever. No, there's more to it than that, folks. This thing is, yeah, he's right in the sense that you can pick any winding for your primary lengthwise, but you still got to figure out. So I first need to show you, I've got a system here which I want to demonstrate to you all. And I've got a big capacitor here, and in real life we don't want it to be this big. It's just because I want to show you the effect. I'll slow it down with the capacitor. So essentially what I'm getting at here is, what we want to do right here is we have our high frequency generator. So we're going to call this high frequency, high voltage. So this could be a very low current neon transformer, whatever, okay? So I'm going to take the output here, and what I'm doing is I'm using a neon to limit to around 100 volts, because this could be really high voltage, you understand here. So on this side here, it goes into my microwave capacitor, which happens to be 1 UF, and it goes back down here, and here we put a diode. So essentially what we got is a half bridge rectifier that will charge at high voltage. Well, we limit it with the help of the neon for the practical of the demonstration here. So on this side here, I have another neon, and it goes out here into a primary winding and then back out here, you see? So what happens now is when we turn this on, the capacitor will want to charge at around 100 volts, and when we get to the trigger, this neon dumps the capacitor across the coil, you see? So we get essentially a crude form of a cap dump circuit here. Now this is very inefficient as it is because it's not tuned. I just used the 1 UF to demonstrate so I can slow down. So when I demonstrate it for you folks, you'll see the neon flashing and you'll see what goes on the scope so I can sync in on time, right? But in reality, what you're going to want to do is figure out what your inductance is, what your capacitance is, and what the frequency is to figure out what capacitor you're going to want to put here. There's a reason for this. You actually want to find a resonant capacitor here. So that'll probably end up being in the NF range. So let's just make it up and say it's 50 NF, which would be, let's say, once we calculated this, okay? So what's going to happen now, folks, is you're going to have an interesting dynamic. Now what happens is we don't need a resonant system to dump the cap in any coil, but what happens is if it's not resonant, it won't be an efficient energy transfer. So that spike you're going to get here won't be as powerful if it were done at resonance. So not only is it faster, but the whole system as an LC circuit will charge a lot faster here and dump thanks to the resonance. Now an additional feature here that some may have clicked in here is when you have an LC circuit, especially with pulse, you end up with a reactive high gain VAR system here. So that's your reactive gains, your reactive power. So you're able to put in very little active power to get some very high reactive power. But in normal circumstances, and especially in radio systems, you can't usually tap into it. As a lot of people mention, you put a diode or something, poof, your reactive gains. So usually it's not accounted for. It's an imaginary kind of gain. But here we're taking advantage of it because it's directly in the LC circuit at resonance. The neon is acting like a spark gap, and it's in resonance. So what happens here is we build up a high reactive VAR here, which charges up the capacitor really quick. And so what I'm essentially saying is we're taking advantage of what we normally can from the VAR, charging this, allowing us at resonance to discharge that gain into our coil here. So something to note here, there is no core. It's strictly RF resonance here. So it's not a typical electromagnetic transformer where we're messing around with flux switching and flux saturation. This field is even all over. It radiates evenly all over. We're not concentrating or directing it in any way, shape, or form here. So essentially what that means here is we can have as many secondaries as we want nearby, acting basically as antennas on the RF end, and we can rectify that or do whatever we want to it, even light up another neon nearby. And how many of these we have, let's say times 3, is not going to stress the additional input load here because we're limited by the dynamics, usually in the milliamps range from these low frequency, high frequency, oscillators. And we're limiting it in here. So this is already tuned with resonance and will do its thing no matter what, and will dump in. So this is essentially the equivalent as why when you have a radio station, it doesn't matter if there's 100 people or 10,000 people listening, it doesn't actually stress the transmitter anymore than having all these additional ones here at resonance. So this all has to be tuned for resonance, of course, to get that effect. So it allows us to take advantage first of the VAR gains, which charges our capacitor, which dumps it. Now what happens is the RF field actually gets generated by the strong inductive kickback you get here, and I will demonstrate that in a moment right here. So right here I use basically a rodent coil or a starship. You be the judge. I don't want to start the discussion. But what was nice here is all of the Ethernet cable are all equal windings. So it makes it a bit easier for resonance and basically ratio wise. So essentially I picked the blue winding and all my additional windings are the same length. So it's basically like tying multiple secondaries in series, and I'm able to better control what I want as an output here by tapping into it. So I have the scope on one of the, so I have serried some of the windings here to do this so I can have a higher output. So what's going to happen is when I turn this on here, this neon is going to limit to 100 volts. It's going to charge the 1 UF microwave capacitor at around 100 volts. I shouldn't say 100, it's more like 90 with the neon. And this one here is going to act like a spark gap and discharge the cap dump into the primary winding. So what you're going to see here is, because this is 1 UF, it's going to take a while. It's going to be like 1 dump a second. So it's going to flash this neon. In reality, for really strong RF fields, you want basically this to seem like it stays on. You want the highest resonant frequency possible to take advantage of this. So as I said, your capacitor is going to be very low value for high frequency. And what's going to happen is that's going to create, now you say, wait a minute, dumping such a small capacitor into a regular coil, you may have tried that experiment before, is not even enough to energize the coil and get an inductive kickback. Well, we're taking advantage of resonance. So at a resonant point, that little not a kickback, but that little trigger will be amplified and come in stronger and induce an even stronger inductive kickback. So we're taking advantage of resonance to be able to use that little tiny cap, which happens to be tuned in resonance, giving you that VAR gain, and that's what's being dumped into the coil, generating a strong RF field that all your secondaries can tap into. So here I've got the 9-volt battery. It's basically a half-dead battery, but it's good enough for the demonstration. So I'm going to turn it on here, but maybe now my 9-volt battery is too dead here for the effect. There we go. So it's dumping, it's blinking. But you see here, the trigger is about 1 volt, and the inductive kickback comes back at about 15 volts here with the spike. It's very quick. But you see the trigger, with the flash. Sometimes it's so fast the scope won't even catch it. But it's about a 1 volt spike, and then you get the kickback. So we're not getting the kickback directly from the trigger. We're just getting the RF coupling part of it, essentially. So this is very slow, not resonant, but even if it's not efficient, my point is, you still get a minor interaction at RF. So it's not costing me any more energy, even though it's not resonant, but we're far from maximizing the effect. I just wanted to use this slow capacitor to show you what happens on the scope here. So it's the inductive kickback on the primary that actually generates the strong RF field. So if you can continue that hundreds of times a second, that generates a very strong field, and it's that we couple into with our antennas. So it doesn't matter at this point how many you have here, it won't affect our input. So we're essentially summarizing everything here. On the input stage, we're making it reactive at resonance. We're actually using the reactive capacitor to dump into one of the antennas, which would be your primary antenna. The inductive kickback generates a very strong radio field, which allows a good interaction with resonant antennas nearby. So no core, just to clarify. And again, this was for demonstration going on very slow. One would want to actually build your own coil at the frequency of your oscillator with your capacitor probably in the NF range. And that would ideally be high voltage into a spark gap system. Now the problem is RF, very noisy. If anyone were to use this method to generate substantial amounts of energy, especially in the USA, the FCC would shut you down, and they have the power to do that. You'd be polluting the spectrum. My recommendation is take this concept, let's go into the high megahertz range, because once you get into like 10, 20 or so megahertz, it's pretty easy to contain and shield it. When you're into the kilohertz range, this stuff will leak and float on any wire confined nearby. It could even go into your mains wiring half a mile down the road, even if it's not directly coupled. And if it's, low frequency, if you're near military and that sort of thing, airports, it could be pretty nasty at high power levels. Okay? I think even at microwaves, if we can incorporate, as I was talking about in other videos, it would be even more efficient. But, to quickly experiment with, I'd say in the higher megahertz, if we have proper shielding, it wouldn't be so bad around the whole device. And there's obviously drastic gains here if you understand what we're doing with reactive power to trigger it, and we're using cleverly the reactive capacitor as the dumping capacitor. You're getting the best of both worlds essentially, with very minimal input to keep this thing going. So again, as I repeat, the big capacitor is totally wrong here. It was just to slow it down to show you the actual dumping mechanism. We still get an inductive kickback, but it's not directly coupled. That kickback was actually a single shot RF field. But imagine that happening hundreds and even thousands of times a second. This would generate a very strong field where several antenna loops could interact and both run their neons and cap dumps without stressing the original input. That's what I'm getting at. But it all has to be tuned, because you have to take your reactive stage here, as I showed in the front, into consideration. This needs to be tuned at the rate it dumps to this. You see what I mean? Then you're in business. This creates a very strong field, and all the nearby antennas could all couple into this now. It's efficient RF resonant coupling. It's not typical electromagnetic field transformer kind of coupling. That's the difference. And that's where your gains really come in. So I hope that I clarified a few points, because I always know people who are interested in this kind of stuff. And I know people keep talking and sometimes they get confused. So I wanted to show you folks a simplified concept and explanation of it all. So again, if you want to take it in this direction, it's another way of getting that spike Bedini was talking about. You see, we're not interested in getting the actual real power here that it takes. We want to use those sharp spikes to generate that RF field that can drive all of these for almost free. this mechanism allows us to do something like that. Now, of course, at higher voltages, take these neons out and put spark gap instead. You're getting into the Don Smith kind of business now, if you can put the pieces together. So again, thank you very much for watching, and I hope this sheds a light on a few questions, and always looking forward to your comments and interactions. Thank you.